So the first thing we want to talk about in this section is hydrostatic pressure. So let's draw some pictures and get some background, and then we'll figure out how we can use integrals to help us resolve some of these types of problems. So let's start with a stationary column or rectangular solid of water. So let's go with the height of this being d. So now let's talk about the bottom surface, which we are going to call A. So the bottom we'll call A. And then this rectangular solid is the volume of the fluid pushing on A. So since we're talking about a fluid, we really want to start talking about force, but we're going to have to do a few computations before we get to force. We know that force is equal to mass times acceleration, or mass times gravity in this case. But the first thing we need is our mass. Well, mass, by definition, is rho times v, where this funky looking Greek letter is the Greek letter rho, and it's the density of the fluid. And v is just going to be its volume. So density times volume gives mass, so the mass of whatever that fluid is. And then we know that force is equal to mass times acceleration, so mass times gravity. So in this case, it's going to be rho times v times g. And if we focus on the volume of this, so for a second we have force is equal to rho times v times g. So the volume of the fluid times its density times gravity. So we know from physics that pressure is equal to force divided by area. So our pressure is going to be our force divided by the area. So using the above, we have our force is equal to this, but note that volume of a rectangular solid would be the area of the base. So that would be our area, right, times the depth d. And that's true for any geometric figure. So if it was a triangular base or something else, it's the area of the base times the height will give you the volume of that three-dimensional solid. So using this in our formula here and substituting our force in here, we get that pressure is equal to rho times g times our volume, which is our A times our D, divided by A, and the A's would reduce out, so we get density times gravity times depth is going to give us our pressure. So it's worth noting in the SI system, the units of pressure are newtons. So if we go back to here, force divided by area, we would have newtons divided by square meters, so meters squared. So a newton per meter squared. This is called a Pascal. So the units of pressure in the SI system are newtons per meter squared, or pascals. In the imperial system, we use atmospheres. So you'll hear them in other ways as well, but for the most part, in these applications, we'll bounce back between the imperial and the SI system, but in all your science classes, they'll use this. So if you're doing any of this in a physics class or something, they're going to always use pascals. Chemistry as well, right? They're never going to give you weird imperial units. Okay, so the next thing that we need, and we are just going to assume this, and it's a fact from fluid dynamics. So fact, we're going to have a couple of these today. So one, at any point in a fluid, the pressure is equal in all directions. So we have this fact. Now we want to ask the question, well, why is this important? So a dam has the shape of a trapezoid. The height is 30 meters, and the width is 80 meters on the top and 50 meters on the bottom. Find the force on the dam due to hydrostatic pressure if the water level is 5 meters from the top of the dam. All right. So as is probably true with almost every application problem, we really should just draw a picture, right? So let's go ahead and draw a picture of this diagram. So we've got this dam, and we know a couple of things about it. So we know it's a trapezoid. It looks something like this. And we know some things about this trapezoid. So we know it has a height of 30 meters. And we know the width is 80 meters on the top and 50 meters on the bottom. So this is 80 and this is 50. We want to find the if we know that the water level starts at 5 meters from the top. So we have this, and we know that it's filled with water, but not all the way. So the dam's not overflowing, which is probably a good thing. So the water level is 5 meters from the top of the dam. Okay. So the idea, and this is similar to things that we've done in previous applications for integrals, is let's imagine we take a strip of our dam, and it's going to have thickness delta x, right? So this is our basic strategy for almost everything. We're going to take a delta x thick rectangle, and we're going to do math on it. And if we can figure out what's going on with this rectangle, then we can use an integral to add up all of the rectangles using the appropriate limits of integration. Okay. So we've got our delta x thick piece, and there's a couple of things we're going to need to figure out. So as we mentioned, we know that we have 30 feet. So I'm going to draw kind of like an axis over here. And then we're going to need to put an origin somewhere. So we have a couple of choices. We can put the origin at the top of the dam, or we can put the origin at the bottom of the dam. And pros and cons of both, but the bottom is going to be the better of these two choices. So if we're going to make the bottom our 0, we then can talk about some distances. So the distance to our strip is going to be x. We know that our water level starts at 25, and we know the top is at 30, which turns out to not be important in this problem. So then we have our distance to our strip is x, and then the distance from the strip to the top is going to be what? Well, if we went x and the entire distance is 25, then this has to be 25 take away x, right? Because then when you add them up, that'll get you to the top of the water. So we have our distance from the strip to the top of the water is 25 minus x, and the distance from the bottom to the strip is x. So now, based on that, we have a couple of things we need to take into account. Is what is going to be, we know it's going to be delta x in its height, but what's the width of that strip going to be? Well, it's going to change, right? So if x is 0, what does the width of that strip have to be? Well, the red strip would then be at the bottom, and what's the width at the very bottom of this container? 50. And if x equals 25, what does the width have to be? We don't know. But what if somehow magically we could get to 30? What do we know the width would have to be? 80, right? So that gives us two ordered pairs, right? So we know when x equals 0, we have the width is 50. And we know, even though this one can't happen, at 30, it's going to be equal to 80. So then, can we come up with an equation that represents our width? Sure. So the first thing we need is our slope, right? So m would be 80 minus 50 all over 30 minus 0, which gives us 30 over 30, which is 1. This guy is going to be our y, or in this case, the w-intercept. So we get that our equation then is that our width as a function of x is equal to 1 times x plus 50, or x plus 50, right? And we can check if I put in x equals 0, I get 50 like I should. And if I put in x equals 30, I get 80, which I should, right? So that seems like it's a good model for what we're doing. So then the area of the strip is its length times its width. Well, its length is delta x, and its width is x plus 50. So we're going to get that our little area, so our dA, is going to be x plus 50 times delta x or dx. I should be consistent. Instead of dA, let's use delta A. It's not really going to matter at the end, but so we have this. So now we have an area, and we need to calculate the force on this. So there's a couple of other things we're going to need to know. So we're told that this dam, and we're going to assume that we're told that it's filled with water, right? So a couple of things, and this will be helpful in our homework. So this is fact number 2. So rho, the density of water, rho is 1,000 kilograms per meter cubed. So this is a converted one because you may or may not know this, but well, never mind. So we'll just leave it with this. I'm getting off into something we shouldn't talk about. All right, so we have our fact number 2, and you will need this in your homework, that the density of water is 1,000 kilograms per cubic meter. So then, if we have our area of a strip, we can then figure out what our change in force is going to be. So the change in force is going to be equal to rho times g times our area times our depth. So times our area. So our area is x plus 50 times delta x times the depth. Right? And we come back to our diagram, and what was the depth of the strip? 25 minus x, right? Because that's how far the strip was from the surface of the water. So then this is 25 take away x. So then finally, this gives us, writing it in terms of differential, so the change in our force, and let's clean this up a little bit, is rho times g times 25 minus x times x plus 50 times dx, right? So I just rearranged all of that stuff around. So that's our force for each little df or dx thick rectangle, right? So basically our strategy was we did exactly what we were talking about up here. We calculated what pressure was. What's pressure? Right? And what's our force? So we just went through and built all of these things by multiplying all of them together, right? So we built our thing, but doing it on a tiny little dx rectangle. So now if we want to add up all of these strips that we've made, we need to integrate. So where would we need to integrate from? Well, we would start at the bottom of the dam, and where would we stop integrating? 25, because that's where the water runs out, right? Because we don't need to integrate from 25 to 30 because there's no water pushing on the dam, right? And we're using the fact because when we're integrating each of these strips, we're actually calculating the force of the water above it. But we know that the force is equal in all directions. So the force pushing down on that is the same as the force of the water pushing on the dam. So this integral is using the fact that we know that the pressure is equal in all directions. All right, so now that we've got all of this together, we get that our force is going to be equal to the integral from 0 to 25, and rho and g are constant, so I'm just going to pull them out in front of my integral. The integral from 0 to 25 of x plus 50 times 25 minus x dx. And now we need to do this integral. So to integrate this, we're going to need to distribute out our polynomials. So let's see, 25x minus x squared. I don't know what 50 times 25 is. Big number. 50 times 25, oops, gives me 1250. And then 50 times negative x is negative 50x. So then gathering up all of our like terms, we're going to end up with rho times g times the integral from 0 to 25 of negative x squared. 25 take away 50 is negative 25x plus 1250. So from here, we just find our antiderivative. So rho times g, and we're going to have negative x cubed over 3 minus 25x over 2 plus 1250x. And we're going to evaluate that from 0 to 25. So from here, I'm just going to put that into my calculator. Yes? Oh, thank you. So from here, I'm going to just put that in my calculator. Oops, I got way too many minus signs. Let's try that again. So x cubed over 3 minus 25x squared over 2 plus 1250x. And then we go alpha trace y of 25 minus y of 0. And y of 0 in this case is actually 0. And we get this value. But that's not the answer, right? Because we get this value, and we have the constants rho times g, right? So our final answer is going to be this times rho g. So then we take our rho and we take our g. So we just grab our calculator. Rho, so our density was 1,000, and g is 9.8. And we press enter. And that gives us our final answer. So remember, when we're in the SI system, we're going to have to multiply by gravity and whatever else we need to. If we're given things in the imperial system, which is going to happen very shortly, we don't have to multiply by gravity, because when we have things given in terms of imperial units, gravity is already part of the computation. All right, so let's go ahead and resolve this. So as always, let's draw a diagram to help us get started. So we've got our pool, and we know that the depth of the pool is 4 meters, and we know that its width is 10 meters, and the water is 0.5 meters from the top of the pool. All right, so now we have to make a choice. Where do we want to put our origin? Okay, bottom, that works. So if we do that, if we make the bottom 0, and then we have our little strip here, the distance from the bottom of the pool to our strip is going to be x, and then the water is at 3.5, so the distance, the depth, d, is going to be 3.5 take away x. So the distance from the surface of the water to our strip is 3.5 take away x. So then the area of our little approximating rectangle is going to be its width, 10 times delta x. I'll just use dx this time. Then the volume of that is going to be this times its height, or its depth, which is going to be right here. So the change in volume is going to be 10 times 3.5 take away x times dx. So then to find our force, we're going to multiply our volume by our density and gravity. So dF is going to be rho times g times 10 times 3.5 take away x dx. And then we need to add up all of these things. So we're going to integrate to find our force, and we're going to integrate from the bottom to 3.5, so from 0 to 3.5. Once again, I've got my rho times my g, and that's going to be constant, so I'll just pull those out. I could pull the 10 out as well, but I'm just going to multiply it in so that I can have 35 minus 10x dx, because then when I integrate that, I'll get some nice numbers. So then we take our antiderivative. We have rho times g. The antiderivative of 35 is going to be 35x, minus the antiderivative of 10x. 10 divided by 2 is 5, so I get 5x squared. And then that's evaluated from 0 to 3.5. So grabbing my calculator, I'm going to put that in for y1. So I have 35x take away 5x squared. And I evaluate that from 3.5 minus 0, well, y of 0, gives us 61.25. So that gives me rho times g times 61.25. So I multiply by rho times g. So rho is 1,000 times g, which is 9.8. And I get 600,250. So if we go back to our original diagram, we decided to put the origin at the bottom. There's no reason we had to. What if we decided that we wanted to put our origin somewhere else. So we still have 10, we still have 4. And we have, now let's put our origin at the surface of the water. So if I make that my 0, and I make positive the downward direction, if I make that 0, then the bottom of the pool is going to be at 3.5. The distance to my strip is then going to be x, right? So if we set this up, we're going to have then that our area is still 10 dx. Our volume then is going to be 10x dx because we're putting our origin at the top. And then our change in force would be rho times g times 10 times x, right? Then what would our limits of integration be? Well, we'd be integrating from the top of the water to the bottom of the pool, so still 0 to 3.5, right? So if we integrate from 0 to 3.5 of rho g times 10x dx, well, that's rho g, and the antiderivative of 10x is going to be 5x squared, and we evaluate from 0 to 3.5. So if we go ahead and do that, let's go 5x squared, and we go y1 minus 3.5, 0. Oh, we get 6125 again, so if we multiply that by 1,000 times 9.8, once indeed, again, we get 600,250. Right? So it just goes to show we have a lot of latitude on where we're going to put our origin. So most of the time, it's not much harder putting it at the top versus the bottom. We will discover that there are some problems where there are places that are better than others to place the origin of our coordinate system. So first observation, you might work a little harder, but you'll always get the same answer regardless of where you put your origin. But as you may have seen in some physics classes before, good choices might make the math a lot easier. So keep that in mind, that if something seems really, really bad, maybe you should try putting your origin somewhere else. It might be a better way to get from A to B. All right, let's take a look at our next example. Example 2, find the hydrostatic pressure on a circular cover on the side of a dam if the center of the plate is 7 feet below the surface of the water and the radius is 3 feet. The density of water is 62.5 pounds per cubic foot. So this time we're given imperial units, so we won't have to multiply by gravity, because pounds already are a force. Pounds already have the gravity multiplied in. So remember, in the imperial system, the unit of mass is very rarely ever used, and it's called a slug. So if they ever give you something whose mass is in slugs, that's the imperial system. All right, so this one we definitely need a picture, because it's not really straightforward what is exactly happening. Okay, so it says find the hydrostatic pressure on a circular cover in the side of the dam. The center of the plate is 7 feet below the surface. Okay, so I've got a circle, and I have its center. That distance is 7 feet below the surface of the water. we know that the radius of this plate is 3 feet. And then we are given the density of water. Okay, we want to find the force on this circular plate. Okay, so let's come up with our approximating rectangle. So let's go ahead and call this, once again, delta x. So now the question is, where are we going to put our origin? Well, we have a couple of choices. The top of the water. There is no real bottom because we don't know where the dam ends. All we know is that the plate's center is 7 feet below the surface of the water. So it turns out in this one, since circles are very symmetric, why don't we put the origin at the center of the plate? So if we put the origin here, we then have something that looks like this. So there's our 0. We have our plate then is located x units. So this distance would be x. And then the distance from the top, from here to here, would then be 7 minus x. So that would be the depth of each of those strips. Okay, so now we've got another problem. Is the width of those strips constant? No, as I move up and down in the circle, when I'm at the center of the circle going through the diameter, it's going to be its widest. And when I'm at the very tippy top of that circle, its width's actually going to be 0, right? So it's going to shrink as we go. So we need to figure out a relationship between some of these things. Well, we know that the standard form for the equation of a circle is x squared plus y squared is equal to r squared. We're told that our radius is 3. So in terms of our variables, x is actually playing the role of y, and we want our width. So w squared plus x squared is equal to 9, and we want the width as a function of x, right? So we're going to minus x squared, we're going to minus x squared, and that gives us w squared is equal to 9 minus x squared. Taking our square root, we get w equals plus or minus, but we really only want the positive, because you can't have negative width. The square root of 9 minus x squared. Okay, so I've now solved for this, but is that actually the width of the entire thing? No, that's only half of it, right? That's essentially half the distance. So the width is 2 times that. So 2 times the square root of 9 minus x squared. And we can check that because at the origin, when x equals 0, if we plug in 0, 0 squared is 0. 9 take away 0 is 9. And what's the square root of 9? 3. So then 2 times 3 gives us 6, which is the distance all the way across, or the diameter of that circle, right? So if we don't double it, we're only getting half of that width, not the entire thing. Okay, so now we have our width. We can actually start. So our area, dA, is going to be our width, which is 2 times the square root of 9 minus x squared dx. So then our force is going to be rho times this, so 2 times rho times 9 minus x squared d. Oh, I'm skipping a step. So I forgot the volume. I'm getting too excited. So then our volume of that is going to be 2 times the square root of 9 minus x squared. And then what's our depth? 7 minus x dx. So that's our volume. And then our force is this times rho. So finally, 2 times rho times square root of 9 minus x squared times 7 minus x dx. So now we need to integrate this thing to find our force. So it's the integral, pulling our constants out, so 2 times rho, and then we're left with the square root of 9 minus x squared times 7 minus x dx. We need to go back up to our diagram, and what are our limits of integration going to be? Well, we need to integrate from the top to the bottom of this disk, right? So here and here. So, well, where's the bottom of that circle going to be? Well, what's its radius? 3. So this is going to be x equals -3. And what's the top going to be? 3. So then we need to integrate this from -3 to +3 to find our force. All right. So now it's time to calculate some integrals. So before we do that, let's multiply and split this up into 2 different integrals. So if I distribute the square root into the binomial, I get 7 times the square root of 9 minus x squared dx minus 2 rho times the integral from -3 to 3 of x times the square root of 9 minus x squared dx. So we've broken it up into the 2 integrals because we don't want the 7 minus x together. So one thing we'll notice is that the first integrand right here, this is an even function. And our second integrand right here is an odd function. The reason that's important is we have a symmetric interval of integration. So to remind us, when we have symmetric interval of integration, when we have an even function, if we have the integral from -a to a of f of x dx when we're even, this is 2 times the integral from 0 to a of f of x dx. And when it's odd, we get the following. The integral from -a to a of f of x dx is equal to 0. And if you don't remember why, let's draw a quick picture for each case. So remember, a function is even if it has symmetry with respect to the y-axis. So if it's symmetric with respect to the y-axis, that means if you fold it over the y-axis, it's the same on both sides. Well, if that's the case, then the area that we would see there indeed would be the same as finding the area of one side and just doubling it, right? Because the area is the same on the left and the right by symmetry. A function is If it's odd, means it has symmetry with respect to the origin. So we get something similar happening again, where our areas are the same, but this time one is above the x-axis and one is below the x-axis. So the area over here would be negative and this would be positive, but by symmetry they're the same, so when you add them up, what do you get? 0, right? So the great news then is, since this is an odd function, we don't even have to calculate that integral. It's just 0. Done. So now we're going to double this integral. So we get 4 times the integral. So we double this, but we got to be careful because there's a 7 on the inside too, right? So when I'm bringing this down, there's going to be a lot of multiplication happening. So what's 2 times 7? 14. And if we double that, it's going to be 28. So we get 28 rho times the integral from 0 to 3 of the square root of 9 minus x squared dx. All right, so now we have to do this integral. So what method are we going to need to do this integration? Well, we have 9 minus something squared. So this is one of our trigonometric forms. So which substitution gives us something squared minus something squared? Sine. So this is x equals 3 sine theta. And dx is going to be 3 cosine theta d theta. So then, getting our new limits of integration, 3 equals 3 sine theta, divide by 3. So that gives us theta is equal to the inverse sine of 1, which is going to be pi over 2. And our next one is 0. So 0 equals 3 sine theta, divide by 3. So theta is the inverse sine of 0, which is 0. So our new integral is 28 times rho times the integral from 0 to pi over 2. And then we have 9 minus 3 sine squared is 3 times 3 is 9 sine squared theta. And then our dx is times 3 cosine theta d theta. So that's the same as 9 times 1 minus sine squared theta. So the square root of 9 is going to be a 3. And 1 minus sine squared is the same as cosine. So we get 3 cosine theta times another 3 cosine theta d theta. So then 3 times 3 is 9. We get 28 times 9 gives us 252 times rho times the integral from 0 to pi over 2 of cosine squared theta d theta. So then to integrate cosine squared, what do we have to use? Cosine squared theta is equal to 1/2 times 1 plus the cosine of 2 theta. So pulling our 1/2 out in front, we get 252 over 2 times rho, the integral from 0 to pi over 2 of 1 plus the cosine of 2 theta d theta. So finally, 252 divided by 2 is 126 rho, and the antiderivative of 1 is theta. The antiderivative of cosine 2 theta is sine 2 theta divided by 2, and we evaluate that from 0 to pi over 2. So that gives us 126 rho times pi over 2 plus the sine of pi divided by 2, because 2 times pi over 2 is pi, minus 0 plus, well, 2 times 0 is 0, so sine 0 over 2. I wrote it theta, but that's a 0. So the sine of 0 is 0. 0 is 0. The sine of pi is also 0. So all of those reduce out. And the only thing that's left is 126 rho times pi over 2. So 2 goes into 126, 63 times. So we get 63 pi times rho. And rho, going back all the way to the very beginning of the problem, the density of water was 62.5 pounds per cubic foot. So 63 pi times 62.5. So 63 times pi times 62.5 gives us that number. So a couple of comments. If you didn't notice it was even and odd and you just did the integral, you'll get the same answer. You'll just work a little harder to get from A to B, right? But finding the other antiderivative, if you did want to calculate this one by hand, the one that we knew was 0, what technique would you have used? Not trig this time. You could do just a u substitution, because u would be 9 minus x squared. Then your du, you have the x on the outside to substitute out. So notice if you did let u equal 9 minus x squared, when you changed your limits of integration, what would they both be? Well, what's negative 3 squared? 9. And what's 9 minus 9? 0. What's positive 3 squared? 9. 9 minus 9 is 0. So you'd integrate from 0 to 0. Oh, well, if you don't have any limits of integration, the area has to be 0 under that curve. So it would have told you that as well when you changed your limits, but you didn't have to do it at all. But like I said before, multiple paths to get from A to B. If you didn't notice it, it'll work out to be 0 all by itself. All right. So now we're going to switch gears. So we're going to switch to moments and centers of mass. Let's start with the idea of what this is. So if we have two point masses, so let's imagine we have a fulcrum. And we have mass 1, we have mass 2. We want to measure the distance from the fulcrum to the mass. So this one's going to be located at the point x1, and this one is going to be located at the point x2. So the idea of the center of mass is the following. Which we will denote as x bar, which is we want to calculate the following, and then we'll talk about what it means. So we want this. So x bar minus x1 and this to be x2 minus x bar. We want the distance from the average to each of the points when multiplied by the masses to be equal. So we would have our mass 1 times x bar minus x1, and we want this to be equal to mass 2 times x2 minus x bar. So the center of mass is the point. We don't know where that is on that diagram, so x bar is going to be somewhere. We don't know, so I'm going to arbitrarily put it here, where if we take the distance from x bar to x1 and multiply it by the mass, we're going to get the same thing as the distance from x2 to that same point when we multiply by the mass. So now if we expand this out, we get m1 x bar minus m2 x1 is equal to m2 x2 minus m2 x bar. Solving for x bar, we get the following. So we add m2 x1, add m2 x1, add m2 x bar, add m2 x bar. Those reduce, those reduce. We get m1 x bar plus m2 x bar is equal to m2 x2 plus m2 x1 So then we can factor out our x bar on the left-hand side. So that's m1 plus m2 times x bar is equal to, I've got a subscript off somewhere. Yep, right here. When I distributed this in, this should have been in m1. That should have been an M1. So in the original problem, I had, when I distributed this in, I had messed up my subscript. So this should have been a 1, this should have been a 1, and that should have been a 1. So let's make sure that we have that correct in our notes. The original one was a 1, but when I wrote it down on this line, I changed it to a 2. So then that makes this an M1 as well. So then on this side, we have M1 X1 plus M2 X2, and we divide by M1 plus M2, and divide by M1 plus M2. So it tells us that the center of mass of that discrete system is m1 times x1 plus m2 times x2 all over m1 plus m2. So there's nothing special about the fact that we did this for two things. Turns out that we could repeat that process for any finite number of particles. So for n particles, we have that x bar is equal to the sum as we see in the numerator, as I goes from 1 to n of m sub I times x sub I divided by the sum as I goes from 1 to n of the m sub i's. So basically what this is saying is if we had three things, x bar would look like this. So m1 x1 plus m2 x2 plus m3 x3 all over m1 plus m2 plus m3. So if there's 10 of them, we're going to sum up all of them and multiply by the masses. All right, so let's go ahead and take a look at our first example. So we want to calculate the center of mass for the system, and we're given a two-dimensional coordinate system this time and some points. So you're probably saying, well, hey, wait a minute. You didn't say anything about two dimensions in the problem that we were doing. Turns out perpendicular axes do not affect each other. So what that means is if we went ahead and plotted some of these points, so we have a 3 kilogram mass at 3, 3, so 3 kilograms, and we have a 10 kilogram mass at -1 and -5, so that's down here at 10 kilograms. We want to find the center of mass. Well, this is really just two different problems. We have the x distance between them, which is going to be this, and then we're going to have the y distance between them. And the beauty of this process is we can treat each of these separately. So if we want to go ahead and find the center of mass in the x direction, we can use this formula. So x bar is going to be m1 x1. So let's start down here. So we have m1, which is 10 kilograms, times x1 in this case is -1, plus m2 times x2. So m2 is 3 times our x2, or out here, is going to be 3, right? Then we need to divide that by all of our masses, and that's going to be 10 plus 3. So that gives us -10 plus 9, so that's -1, over 10 plus 3 is 13, right? So that's our x bar, and we got that by using only our x coordinates, right? So our x value and our x value. We can then calculate our y bar by doing the same thing. So we have our 10 times our y value down here is -5, plus 3 times our y value, which is 3, all divided by our mass, which is 10 plus 3. So that gives us -50 plus 9 is -41 all over 13. So -41 over 13 is going to be a little less than -3. So we'll say about -3. And the other one's -113 is pretty close to 0. So it puts our center of mass at about this point. And that's just approximately, right? Because those aren't exact numbers. -41 over 13 is not -3. It's a little bit less than -3, right? But it's a reasonable approximation. So when we look at that picture, does that seem to make sense? We look at our x bar and our y bar, and our x bar seems to be, well, is less than 0, but the 10 kilogram mass is having an outsized effect on its location, right? Just like your 5 credit class is going to have a bigger effect on your GPA than a 1 credit class, right? So that's why the center of mass here is closer to the 10 kilograms. Similarly, we get the same thing in the y. Everything got sucked down towards the 10 kilogram mass. All right, so what's happening next? So we've got some facts that we need to talk about once again. Let's see if we can generalize this idea using integration to something that's not discrete. So in our previous example, we used the fact that we had these point masses. So let's take a look at fact number 1, and then we'll see if we can figure this out. So if a rectangle has one corner at the origin and the opposite corner at diagonal w, L, and constant density, it has a center of mass of w over 2, L over 2. Let's see if we can figure out why that's the case. So let's draw our picture and see what we can come up with. So we've got a rectangle that looks like this, W, and we have L, and we want to find its center of mass. Well, we know that this plate now has constant density, and we claim that its center of mass is going to be at its geometric center. Well, how could we justify that? Well, if you thought about trying to balance it like we were talking about on a point, if you wanted this thing to balance, where would it have to be? If you're in the teeter-totter, if everything's equal, you need it to be the same on all sides, right? So this is really just that idea that if you wanted to balance something that had perfect symmetry, you'd need to put it at its exact center. So it gets trickier if you don't have constant density, but that's a different story altogether. So we've got something that looks like this, and now we want to figure out, well, how can we use that to bootstrap up to a general curve? Well, if we know how to find the center of mass of one rectangle, if we want to find the center of mass of some curve, so something that looks like this, right? The idea then is we can use an integral, right? So if we were going to do that for each approximating rectangle, we could come up with our center of mass, to get this. So let's see if we can figure out, first of all, well, what would our mass be? So if we wanted to find the mass of this region, how could we do so? Well, we know from our previous work that mass is equal to density times volume, or in this case, density times area, right? So this is going to be density times area. So then that's just going to be density times the integral of f of x dx, right? So our mass is just going to be the density times each of these things. All right, so we want to come back and look at what we had up here. So there's a couple of things we want to notice, and we want to draw some analogies. So in x bar and y bar, what did we notice about the denominator when we did it for the discrete system? What was our denominator in both fractions? 13. And what was 13? Well, what was the mass of M1? 3. And what was the mass of M2? 10. So 13 was just the sum of all of the masses. So we want to make some observations. So the coordinate of the center of mass is going to be x bar is equal to, we're going to do m sub y over little m, and we'll define what each of these mean, and y bar is equal to m sub x over m. So we've already talked about these guys right here, which are the same in both. So that's going to be the mass of the system. But now we've got this new symbol, m sub y and m sub x. Well, what did we do in the top? So when we look at this, here's the sum of our masses, right? To find x bar, what did we do in the top? We multiplied all of the masses by their coordinates. So we're going to refer to this as the moment. So when we say m sub y, we mean the moment about the y-axis. So the reason we call it the moment about the y-axis is we're talking about the x distances, right? So we're talking about the distance from here to here and the distance from here to here, right? So if you think about it, we're talking about the distance from the y-axis because the x is perpendicular. The x distance is the perpendicular distance from the y-axis. So that's why we use the symbol m sub y, is we're talking about the perpendicular from the axis of rotation. Similarly, when we have y bar, we talk about m sub x, right? So this would be the moment about the x-axis. So we have our moments, and we're really just talking about the perpendicular distance from that axis. So now let's fast forward back to where we were. So we've got this arbitrary rectangle. So we have our mass, which is going to be just rho times the integral of the area of the curve. But now, what would be the moment of this rectangle right here about the x-axis? So let's take a look at our moment right here. So what would our m sub y need to be? So we're treating it as if it is at the center of mass. So we're going to have the sum over all of our rectangles, how many ever of those we have. And then we're going to need its area. So what's the area of one of these rectangles? Well, what's its width? Delta x. And what's its height going to be? Well, whatever f of x bar is. So f of x bar. So this gives us our area. But to find the moment, what did we need? When we did it up here, it was the mass, so density times area. So our mass times its distance from the axis. So how far is the center of that rectangle from, oh, sorry, we're actually going this way. We're doing m sub y, so I've got my arrow the wrong way. How far is this from the y-axis? Well, that's just the center of mass, right, which is located at x bar. So then that's going to be times x sub I bar. And that's our distance. So then we have our area. So then finally, to finish this, we need a mass. So we have our density. So that gives us our moment about the y-axis. So now let's see if we can calculate the moment about the x-axis. So if we do m sub x, we're going to have the same summation again. We're going to have to do the same idea. So the area of those rectangles didn't change, and their density didn't. So we're going to have rho times delta x times f of x sub I bar. So this is going to be all together, that's our mass, right? Because it's area times density, just like in the previous problem. But now we have to figure out our distance. What is the distance from the x-axis to the center of mass of that rectangle? Well, what was the height of the whole rectangle? F of x, right? So what's the halfway point? You cut it in half. You divide it by 2, right? So then we get that this is going to be then f of x sub I bar over 2. So then cleaning both of these up just a little bit, our m sub y, well, let's do it this way. So if we have all of these things, if we let n go to infinity, our Riemann sums are going to converge to integrals. So we're going to have in this one x times f of x. So we get m sub y is going to be equal to the integral from a to b of our density times x times f of x dx. And our m sub y, as n goes to infinity, is going to be the same thing, the integral from a to b of rho, but this time we have f of xi bar times f of xi bar, and we have a 1/2. So we're going to have rho over 2 times f of x sub I bar squared dx, right? So we have an f of x sub I bar and an f of x sub I bar, and that will be the integral equivalent of each of these. So our moment for the y-axis is rho x f of x dx, and our moment for the y-axis is rho over 2 times f of x, sorry, this should just be f of x squared. And then our mass, little m, is just the integral from a to b of rho times f of x. That's just our area times our density. For almost all of the problems we are going to run into, we are going to have constant density. So that means we'll just be able to pull the density out of the integral. If for some reason the density is a function of x, then we would have to leave it in, right? Okay, so now we've got all of these, and if you look in your notes, they're actually all summarized right here. And then we get, as well, the formulas for x bar and y bar, which are essentially the same formulas that we had above, but now instead of using the sums, we're actually going to use the integral version, which is just to add up all of those approximating rectangles. So x bar is m sub y divided by m, which is the integral from a to b of rho x f of x dx divided by the mass, and so forth. All right, so let's go ahead and use these to find the center of mass of this region. So in order to do this, the easiest thing to do is to calculate mass, my, and mx. So let's calculate each of those, and we have that the center of mass, we want the center of mass of the shaded region below, and our density function is just 3 grams per centimeter squared. So our density, for all intents and purposes, isn't going to change. It's always going to be 3, right? Okay, so let's calculate our mass first. So our mass is going to be the integral from, and we need to do a little bit of work. So it looks like we have a circular part and a linear part. So we need to figure out each of these equations. So what is the radius of this circle right here? So that's a circle, and it has radius, it looks like, 2. Like if we kept, wow, that's terrible, but you get the idea. That's what our circle would look like. So the equation of a circle with radius 2 is x squared plus y squared equals r squared, so 2 squared. So x squared plus y squared equals 4. And we solve for y, so minus x squared. We get y squared is equal to 4 minus x squared. Taking our square root, we finally get that y is the square root of 4 minus x squared. We now have our second piece that we're looking for, and this one's a lot easier. We have a straight line that starts at the y-intercept of 0, 2 and has x-intercept 2, 0. So what's the slope of that line? -1. And what's its y-intercept? 0, 2. So then the equation of that line is y equals negative x plus 2. Right? We can check that by plugging in 0. We get 2. And if we plug in 2, negative 2 plus 2 is 0. Right? So we have each of these equations. So now we need to calculate our mass, right? So it's instructive to think about this. We only want the mass of that shaded part, right? If I do the integral of the curve in red, what am I going to be finding the mass of? Everything below that curve, which would even include this part down here, right? Which I don't want. So then I would have to subtract off that region, but wait, that's just going to be the integral or the area underneath the line, right? So just like when we were finding the area between two curves, what's our strategy? Upper minus lower, right? So our integral is going to run from 0 to 2 of our density, and since our density is constant, I'll just pull it out in front. So we have our density is 3. So that's rho. And then we have our upper curve and our lower curve. But what's our formula? M sub y is rho x, f of x. So we're going to have x times 4 minus x squared minus x times our other curve, which is going to be negative x plus 2 dx. So that's going to give us our mass, and we can break this into two integrals. So 3 times the integral from 0 to 2 of x times the square root of 4 minus x squared dx minus 3 times the integral from 0 to 2. And let's distribute this in. In fact, if we distribute the negative x in, we get x squared minus 2x dx, right? So how are we going to do the first integral? What technique do we need to integrate x times the square root of 4 minus x squared?
Trig sum.
Great idea, but we can get away with something easier. The trig sub will work. You'll just work harder than you need to. Since we have the x
sub.
on the outside, we can just do a u sub.
U sub.
Yeah, perfect. So we do u is 4 minus x squared, and then du is going to be negative 2x dx. So then we divide by negative 2x, and we divide by negative 2x, and we get our dx is equal to negative du over 2x. And then we have to change our limits of integration. So u of 0 is 4 minus 0 squared, so that gives us 4. And u of 2 is equal to 4 minus 2 squared, which is 0. All right, so that's our first part right there. So let's go ahead and do that. So we have 3 times the integral. Our new lower limit of integration is 4, and our new upper limit of integration is 0 of, and now we substitute out, we have our x times the square root of u, and then dx over negative 2x. Our x's reduce out, as they should, plus our other integrals just coming along for the ride, right? We haven't done anything to this second part yet, and we have x squared minus 2x dx. And sorry, I wrote dx there, but we substituted dx out for u. So now we've got a minus in our integrand, so if we change it to a positive, we can reverse our limits of integration and pull our 2 out in front. So we get 3 over 2, and now we have the integral from 0 to 4. Rewriting the square root of u as u to the 1/2 du. So remember, you get the negative of the integral if you reverse the limits of integration. So to get rid of that minus with the minus 2, we just reversed our limits of integration. And then plus 3 times the integral from 0 to 2 of x squared minus 2x dx. All right, so now let's finally do this. So we have 3 over 2 times the antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2. Well, that's convenient. They reduce out. Plus 3 times the antiderivative of x squared is x cubed over 3, and the antiderivative of negative 2x is negative x squared, and this is evaluated from 0 to 2, and this one's evaluated from 0 to 4. So we get 4 to the 3 halves minus 0 to the 3 halves plus 3 times, and we get 2 cubed over 3 minus 2 squared minus, we put in 0, we're just going to get 0. So then we get 4 to the 3 halves. 2 cubed is 8/3 minus 4. But if we just distribute our 3 in, we're going to get 8 minus 12. So we get 4 to the 3 halves minus 4. And 4 to the 3 halves can be simplified. So what is 4 to the 3 halves?
8.
8. And there's a few different ways that we can realize that. So one is it's the square root of 4 cubed minus 4. 4 cubed is 64, and the square root of 64 is 8. 8 minus 4 gives us 4. Right? So that's one way. We can also just put it all into our calculator, right? And we'll end up with what we need. All right, and I'm also a liar face. I didn't find our mass. What did I find? I multiplied by x. When I multiply by x, what am I finding? I found m sub y, right? So I'm a liar face. This one's not our mass. This is m sub y. To find just our mass, what would we have to do? Our mass is just the integral. So the integral from 0 to 2, and it's just going to be our density times all of this. So 3 times the square root of 4 minus x squared minus our line, which was negative x plus 2. All right. So then this time, when we want to calculate this, we are going to need to do our trig substitution, right? Because our first one we can't do without the trig substitution. So let's break this into two integrals once again. So 3 times the integral from 0 to 2 of the square root of 4 minus x squared dx. Distributing our minus in as we break it up gives us x plus 2 dx. So that second one's going to be easy. This first one, we do need to do our trig sub. So we make x equals, and if we have a constant minus x squared, that's going to be our sine form. So it's going to be 2 sine theta. And then dx is going to be 2 cosine theta d theta. And we change our limits of integration. So we have 2 equals 2 sine theta, divide by 2, divide by 2. And that gives us theta is equal to the inverse sine of 1. And that happens at pi over 2. And then we have 0 equals 2 times the sine of theta. We divide by 2, divide by 2. So then theta has to equal the inverse sine of 0, which is 0. And we substitute. So we get 3 times our integral from 0 to pi over 2 of the square root of 4 minus 4 sine squared theta times dx, which is 2 cosine theta d theta, plus this other integral, right, that we haven't even touched yet. And it's got a typo in it. When I distributed that minus sign in, this integral should have been x minus 2. So here, when we distributed that minus sign in, the negative made that positive, and the negative positive made that negative. And I had written that down incorrectly. So now we simplify this by factoring out our 4 times 1 minus sine squared theta. And what's 1 minus sine squared theta the same as? That's cosine squared. So this gives us the square root of 4 times, or square root of 4 cosine squared theta. So that just simplifies to 2 cosine theta. So I'm going to have the integral from 0 to pi over 2 of 2 cosine theta times another 2 cosine theta, d theta, plus 3 times this integral that's still here. So 2 times 2 is 4 times 3 is going to give us 12. Times the integral from 0 to pi over 2. And what's cosine times cosine? How do we integrate cosine squared? We use our 1/2 times 1 plus cosine 2 theta d theta plus 3 times this guy. So finally, we're ready to do this antiderivative. 12 times 1/2 is 6. And the antiderivative of 1 is theta, plus the antiderivative of cosine 2 theta is the sine of 2 theta divided by 2. And we evaluate it from 0 to pi over 2, plus we have 3 times our antiderivative here, which is x squared over 2 minus 2x, and evaluate that from 0 to 2. So that gives us 6 times pi over 2 plus 2 times pi over 2 is the sine of pi over 2 minus 0 plus the sine of 0 over 2 plus 3 times, we plug in our 2, so 2 squared over 2 minus 2 times 2, and then when we plug in 0, we're going to just get 0. So minus, we'll just put the 0 because I'm running out of space. So we finally get to simplify all this. The sine of 0 is 0. All those are 0. And we end up with 6 times pi over 2 is 3 pi plus 2 squared is 4 over 2 is 2 minus 4. So that's going to be negative 2, and negative 2 times 3 is negative 6. All right, so, okay. Would you believe me if I said we just did that like the super long way? Sometimes we get so busy thinking about calculus that we forget. What is this red graph again? Oh, it's a circle of radius 2. Do we have a full circle? No, it would be a quarter of a circle. So what would the value of that integral be? 1/4, and what's the area formula for a circle? Pi r squared. Our radius is 2. Pi times 2 squared. 2 squared is 4. And then we have our quarter of a circle, gives us pi. And then we can calculate off the triangle beneath it. And what's the area of this triangle? Base and height are 2, and what's its area? Well, 1/2 base times height, so its area is going to be 1/2 its base times its height, so it's going to be 2. So I get the area of my circle is pi, and the area of that triangle is 2, and I have to subtract them, right? So I get pi minus 2. And what answer did we get? What's the 3? Oh, that was our density, right? Area times density gives us mass. So we did all that crazy math, but if we would have just realized geometrically what was going on, we were finding the area of a circle and the area of a triangle, right? We know how to find the area of a circle, and we know how to find the area of a triangle. So don't reinvent the wheel if you don't have to, right? So if you realize something's a circle, use the area formula for a circle. That's what an integral is. Well, it's one of the many things that it is, but it is just an area, right? So the reason I like to mention this is sometimes we get so caught up in doing integrals and thinking about them, we forget what the object actually is, and sometimes there's a lot easier way, right? We just, oh, it's a circle. I know how to find its area. Ta-da, I'm done. And that would have saved us how much work? Okay, kind of a lot, right? So let's see. We've got our mass. We've got m sub y. And what's the only thing that we have left then? M sub x. And our formula for m sub x is the integral from 0 to 2 of rho over 2. So that's going to be 3 over 2, f of x squared minus g of x squared. So our f of x is the square root of 4 minus x squared minus our g of x, which is negative x plus 2 squared dx. Well, that squaring makes a lot of things work out rather nicely. So 4 minus x squared squared is just going to be 4 minus x squared. Minus minus makes it plus x minus 2 dx. So further, we just keep cleaning up what we have. And we end up with, oops, sorry, I got a little out of control there. This guy's squared. We got to do a little math first, right? So we have negative x plus 2 squared, so negative x plus 2 times negative x plus 2 is x squared minus 2x minus 2x plus 4. So that's going to be x squared minus 4x plus 4. And then we got to distribute that minus in. So minus x squared plus 4x, take away 4 dx. So now we get to clean some things up. The integral from 0 to 2, we have negative 2x squared, and then a positive 4x, and then 4, take away 4 is 0, so they reduce out, and we're left with the following. So let's integrate this thing. So 3 over 2 times negative 2/3 x cubed plus 2x squared, and we're going to evaluate that from 0 to 2. So that's going to be 3 over 2 times negative 2 over 3, and we plug in 2 cubed plus 2 times 2 squared. And when we plug in 0 to both of those, they're just going to be 0. So this is really just calculator food at this point, right? So let's just feed that to our calculator and see what we get. 3 over 2 times negative 2 over 3 times 2 cubed plus 2 times 2 squared, close our parentheses, we get 4. Oh, that worked out nicely. So we get 4. So now let's summarize all of the things that we had. So our mass m was 3 times pi minus 2. Our m sub y was, what did we come up with? 4. Oh, and our m sub x was also 4. Well, that's convenient. So then x bar is equal to m sub y divided by little m. So that's 4 over 3 times pi minus 2. And y bar is equal to m sub x over little m, our mass, which is also going to be 4 over 3 times pi minus 2. And that gives us the center of mass of that region. So the moral of this story is the integrals can be a little bit complicated, but at the end of the day, to find x bar, we need m, y, and m. To find y bar, we need mx and m. Okay.